So now we're going to talk about phase diagrams, which is a graph which plots pressure versus temperature as a function of the phases of a particular substance, solid, liquid, and gas. So here's the boundary between the solid and the liquid state. So this would represent the melting point or the freezing point of water in this case at a particular temperature. And of course, at 1 atmosphere, water freezes at 0 degrees Celsius. 0 degrees Celsius. So the intersection is right there. But if we wanted to know when water would boil at a higher pressure, we'd just look on the phase diagram and drop down to the corresponding temperature. Likewise, between the liquid and the gas, you're talking about the boiling point, or condensation, if you're going from the gas to the liquid. And here's the boundary of that. So again, at 1 atmosphere pressure, boiling occurs at 100 degrees Celsius. But if you wanted to know the boiling point at a higher pressure, you just look at the phase diagram, you'd find the pressure and drop down to the temperature. The boundary between solid and gas represents the boundary between sublimation, going from the solid to the gas, or deposition, going from the gas to the solid. So this represents the sublimation curve, this is the fusion or melting curve, and this is the vaporization curve. By the way, if you're ever given a phase diagram without solid, liquid, and gas being marked on it, just the boundaries here, you can easily figure out which is the solid, which is the liquid, and which is the gas without memorizing this. Just remember that at very cold temperatures and high pressures, it's probably going to be a solid. So if you're way over here with cold temperatures and move up to higher pressures, you're talking about a solid. And then, of course, the gas is going to be the phase in evidence when you have high temperatures and low pressures. And the liquid will be between them. That's an easy way to remember solid, liquid, and gas on a phase diagram. Now, there is a point where the three phases are in equilibrium, and that's called the triple point. It's right there where the three boundaries meet. And at that pressure and temperature, all three phases of water, in this case, would coexist. There's also, if you follow the vaporization curve all the way up, you get to the end of it, and it's called the critical point. We'll show you what that means in a little bit, but it's where the liquid becomes supercritical, and the boundary between the gas and the liquid disappears. So, as I said, note the melting point at 1 atmosphere, note the boiling point at 1 atmosphere, and in water, note the slope of this line, the boundary between solid and liquid, is a negative slope. That means that under higher pressure, the freezing point becomes lower, not higher. This is extremely unusual. Usually, for almost all other substances, you put it under pressure and the melting point increases. But with water, you put it under pressure and the melting point or the freezing point decreases. The reason is that the density of ice is less than that of pure water, and that's why ice floats instead of sinks. And again, there's only 1 or 2 other substances in which the solid is less dense than the liquid. And that's exactly the reason why this boundary between solid and liquid has a negative slope, not a positive slope. So here's a close-up of the phase diagram of water. And let's show you how you use a phase diagram. Here we're starting with ice at minus 25 degrees C. And we warm it up and warm it up, approaching the boundary between solid and liquid. When we get to the boundary line, the temperature stops changing as the phase transition progresses. After all the ice has melted and we continue warming the liquid, we now move into the liquid portion, and we can travel all the way to 100 degrees Celsius, where we get to the boundary between liquid and gas. At this point, we have boiling. The temperature stops changing until all of the water has boiled away into steam. Then, if we collected the steam, we could actually superheat it and make it hotter than 100 degrees Celsius. Or you could track the phases involved at various pressures instead of the phases involved at various temperatures like we just did. If we're at 1 atmosphere and 25 degrees, we have liquid water, and we begin to lower the pressure, lower the pressure. Eventually, there's a point where the water will begin to boil, and that will occur at this pressure right here. If we track over and see what pressure that actually is. In contrast to water, I wanted to show you the phase diagram of carbon dioxide. And here you can see a positive slope on the boundary between solid and liquid. As you put carbon dioxide under pressure, solid carbon dioxide or dry ice, the freezing point becomes greater, not less. And that's how it is with most substances. But look how cool this is. At 1 atmosphere, if you track along this line here, you go directly from the solid to the gas. Hello? That's why it's dry ice. Because at normal pressure, 1 atmosphere, you completely bypass the liquid phase, right? So you go directly from the solid to the gas. The dry ice absorbs energy and keeps your ice cream frozen. Yeah? If you wanted to see liquid carbon dioxide, and by the way, if you just take any of these fire extinguishers, that's a CO2 fire extinguisher, and shake it, you'll hear a liquid sloshing around. It isn't dry ice in there, it's liquid carbon dioxide. And it's got to be over a pressure of 5.1 atmospheres. Only above that threshold will liquid carbon dioxide be able to exist. Now let's answer some questions about phase diagrams. I'll ask you these in class, so think about them. Which area represents the solid state and which the gaseous state in this first picture here? And what point is the triple point? A, B, C, or D? Which line represents the boiling point at various pressures? And in which phase diagram does the melting point decrease as pressure is applied to the solid? This one or this one? Let's turn our attention to supercritical fluids. If we keep adding pressure to a liquid in a sealed container and keep heating it, more vapor collects, causing the pressure inside the container to rise. And the density of the vapor increases, and the density of the liquid decreases. And you get to some temperature where this meniscus, or boundary between the liquid and the gas, disappears. And at that point, you have a supercritical fluid. A supercritical fluid has properties of both gases and liquids. Now, let's talk about attractive forces and solubility. Solubility depends on the attractive forces of solute and solvent molecules. And the little mnemonic is that like dissolves like, which means substances with similar polarities dissolve in each other. When two liquids are soluble, there's no boundary line when they are mixed, and they're said to be miscible. They dissolve in each other. And you can be assured that they have similar polarities. Polar substances dissolve in polar solvents. They might have a hydrophilic group, which means a water-loving group. Hydroxide, C double bond O, COOH, NH2, even chloride are groups that help to make a solvent a polar solvent. Nonpolar molecules dissolve in nonpolar solvents, again, like dissolves like. So you might have a molecule primarily of carbon-hydrogen bonds or carbon-to-carbon bonds, oil, gasoline, and the like. These will not dissolve in water, but they will dissolve in each other. Many molecules have both hydrophilic and hydrophobic parts. They might have polar groups on them, like OH or C double bond O, and the structure of the molecule might have a lot of carbon-to-carbon bonds, which makes it nonpolar. And when a molecule has both hydrophilic and hydrophobic parts, the solubility becomes a competition between the parts. Here's an example. If you take water and pour on top of that the hydrocarbon pentane, you get two layers. The pentane being less dense is on top, the water being more dense is on the bottom. They do not dissolve in each other. Let's take a look at some polar solvents. Of course, there's water. It's polar because of the shape of the molecule and the fact that oxygen is quite electronegative, hydrogen is not, so the oxygen-hydrogen bond is quite polar. Then the asymmetric shape of the molecule means that it has a positive side, the hydrogen side, and a negative side, the oxygen side. Another example of a somewhat polar solvent, much less so than water, is methylene chloride, or dichloromethane. It's a carbon attached to two electronegative chlorine groups. That makes these bonds polar bonds. And again, it's a lopsided molecule, so this is the negative side of the molecule with the chlorines, and this would be the positive side. Ethanol, or ethyl alcohol, is also a polar solvent. It's got two carbons, and then an oxygen and a hydrogen. And of course, the OH group is the polar side of the molecule and can attract another ethanol molecule to it because it has a positive side and a negative side. You get these attractions, so that ethanol is very soluble in water, completely miscible with water because of its OH group and the fact that its hydrocarbon part is quite short. Here are some nonpolar solvents. N-hexane, that's a carbon chain with 6 carbons, very nonpolar, and it will not dissolve in water. Carbon tetrachloride is a carbon atom bonded to 4 chlorine atoms. And even though these bonds are polar bonds, the whole molecule is symmetrical, so there's no net positive side and negative side, and the molecule is very nonpolar. Here's another hydrocarbon, an aromatic compound it's called. This ring is an aromatic ring. Toluene, very nonpolar. So we mentioned that like dissolves like. Charged particles, ions and dipoles, tend to be soluble in each other because their particles attract each other. Here's water and strong attractions between water molecules. Here's methanol. Again, hydrogen bonding is possible, like in water. You have an OH bond. The hydrogen is positive, the oxygen of another molecule is negative, and there's an attraction between them. And if you pour methanol in water, then the methanol molecule can hydrogen bond to the water molecule. So methanol is completely soluble in water, as is ethanol, with an alcohol with one more carbon. We all know sodium chloride dissolves in water, And that's because the water molecule, being a dipole, is able to surround a negative chloride and a positive sodium ion. The positive side of the water molecule surrounds the chloride ion, which is negative. And the negative side of the water molecule surrounds the positive sodium ion. So you end up with sodium chloride being very soluble in water because water has such a strong dipole. Nonpolar molecules like naphthalene, better known as mothballs, dissolve in nonpolar solvents like hexane via dispersion forces, temporary induced dipoles. So here is naphthalene. These will dissolve in hexane, heptane, a hydrocarbon, because they're able to attract each other with dispersion forces. So here are some questions for you that we'll do in class. Which is more soluble in water, iodopentane or propyl alcohol? Or which is more soluble in water, butanol or pentanol? And in which solvent will sodium chloride be more soluble, methanol or propanol? You probably know this alcohol as rubbing alcohol. This is methanol with 2 carbons and a hydroxide. That's ethanol, the active ingredient in beer and wine and alcoholic spirits. And with 3 carbons, you're talking about rubbing alcohol. This is ethylene glycol. In which solvent will ethylene glycol be more soluble? In hexane or in water? Surface tension is the tendency of liquids to minimize their surface area, which creates a kind of skin at the surface that resists penetration. Do you see how surface molecules of the liquid have fewer neighbors than interior molecules? If these molecules have significant interparticle attractions, and water certainly does with its hydrogen bonding, that makes the surface particles inherently less stable than their interior counterparts, with a higher potential energy. This is because strong interparticle attractions have lower potential energy, and this energy inequity causes the liquid to minimize its surface area. Also, increasing temperature reduces surface tension. Capillary action is the ability of a liquid to flow up in a thin tube against the influence of gravity. The thinner the tube, the higher the rise will be. It's caused by 2 factors: the cohesive forces that attract the molecules together, and in water's case that's going to be hydrogen bonding, and then the adhesive forces that attract the molecules on the edge to the tube's surface. In the case of glass, glass is a network of silicon and oxygen atoms and can engage in one-way hydrogen bonding, where the hydrogens of water molecules, which are slightly positive, are attracted to the electronegative oxygen atoms of glass, which allows water molecules at the edge to creep up the sides of the tube, creating water's familiar meniscus. And more important, capillary action is also the primary mechanism by which plants absorb water and the nutrients dissolved in the water. When water freezes, it sets up an open hexagonal structure of ice, which keeps water molecules further apart on average than in water. And because of that, ice is less dense than water and ice floats. This is a very unusual quality because almost all liquids, other than water and a couple of other substances, the solid phase of that substance sinks in the liquid phase. You can see the hexagonal nature of solid ice in a snowflake. Back in the day, there was a lot of student interest and participation in environmental issues. We've mentioned several of water's unique properties: heat of vaporization, surface tension, density of ice versus liquid, and so forth, that make it especially fit to support life. Since I and some of my friends were into photography, I put together a slideshow that relates how each of water's properties helps life to thrive. After the first 10 minutes or so, with concepts that you are required to know and will be tested on, I present a picture show of the hydrologic cycle, the way water continuously is recycled in the environment. While that section is not required, I left it in because some of you may enjoy it.
Of all substances on Earth, the simple molecule water is one of the most important for all life. This statement applies to the water of our external surroundings, known as the hydrosphere, as well as the water within living organisms. About 71% of the Earth's surface is covered by water: lakes, streams, groundwaters, and, of course, the oceans. We might infer that this simple compound of hydrogen and oxygen is important to life solely on the basis of its abundance in the biosphere. But even more significant is the remarkable fitness of water for the conditions of life within and without the living organism. No other substance even approaches water in appropriateness of its properties to living organisms and their interactions with their surroundings. While a biologist may look at an organism and ponder its adaptability to its environment, let us, as chemists, turn this question around. What is there about the environment, water in this case, that makes it so specially fit to support life? We need to examine 5 of water's properties to help understand its fitness. Those properties are heat capacity, heat of vaporization, densities of ice and water, surface tension, and solvent properties. Water's thermal properties are uniquely suited to moderate temperature. The heat capacity of liquid water is defined as the amount of heat, in calories, needed to raise the temperature of 1 gram of water, about a half a thimbleful, 1 degree centigrade. This amount of water, for a 1 degree change, requires 1 calorie of heat energy. Most other substances have lower heat capacities than water. This means water tends to absorb a lot of heat compared to other substances before its temperature actually changes. Now, temperature is one of the most critical factors affecting life on Earth. Anyone who has experienced a high fever, just a few degrees warmer than normal, knows this. Although man has devised ways to protect himself from temperature extremes, most organisms can survive only within a narrow range of environmental temperature. The high heat capacity of water tends to minimize temperature fluctuations, especially in large bodies of water. Fish and other aquatic animals rarely have to tolerate large temperature changes. Large bodies of water also moderate the climate of surrounding land. Compare the summertime temperatures of San Francisco with California's scorching Central Valley. Another way in which water moderates temperature is by virtue of its extremely large heat of vaporization. It requires 540 calories of energy to convert 1 gram of water to 1 gram of steam at 100 degrees centigrade. Most other substances have much lower heats of vaporization. Even more than the high heat capacity, it is the heat of vaporization and its reverse, the heat of condensation, that stabilize the temperature of organisms and their environment. Every gram of water evaporated absorbs 540 calories of energy, and when that water vapor condenses back to the liquid, those 540 calories are released. So in tropical areas receiving lots of sunshine, every 14 drops of water that evaporate absorb 540 calories of solar energy, helping to cool that region. Winds then blow the gaseous water to cooler climes where the vapor condenses, and the droplets coalesce to form clouds. As soon as that gram of water vapor condenses back to the liquid form, it releases the 540 calories absorbed at the equator, helping to warm the region. A chart which compares marine temperatures and continental or inland temperatures clearly reveals water's moderating effect. Note that at 0 degrees latitude, the equator, the average continental temperature is 34.6 degrees centigrade, but the average marine temperature is 26.1 degrees centigrade. At the poles, latitude 90 degrees, the average continental temperature is minus 26.1, but the marine climate is minus 8.7 degrees centigrade. As mentioned before, it is particularly important to protect the complex molecules of life within an organism from temperature change. Water makes up 80 to 90% of the weight of the cell, the fundamental unit of life. So, while water's high heat capacity makes internal temperatures resistant to temperature change, evaporation of water is a particularly efficient way that perspiring animals and transpiring plants cool themselves. Every gram of water that vaporizes removes about 540 calories of heat from the organism. This pipe cracked when the water in it froze overnight. Water expands when it freezes. The solid phase is less dense than the liquid phase. In other words, ice floats. Very few other substances share this rather unique property, which again affirms water's fitness to support life. Because ice floats, bodies of water freeze from the top down, not from the bottom up. The top layer of ice insulates the underlying water from heat loss to the atmosphere, thus slowing down the further freezing of the body of water, allowing aquatic life to survive through the winter. Because water is most dense at 4 degrees centigrade while still a liquid, every autumn convection currents bring cooler oxygenated water to the bottom of the lake and bring the warmer nutrient-rich bottom water to the surface. Of course, the expansion of water on freezing is an important tool in the weathering of rocks. The shattering of rock by frozen water aids erosion, one of the primary agents for soil formation. The surface tension of water is extremely high compared with most other substances. Surface tension is directly linked to the ability of the fluid to be drawn up in fine tubes, a phenomenon called capillary action. Plants in this way receive their nutrients dissolved in water and drawn up through the tiny fibers of their roots. Water has been called the universal solvent. Indeed, it has carved much of the Earth's land surface. But water is also capable of dissolving the myriad of compounds which keep life going. As a solvent, water plays two major roles within organisms. It acts as the transport medium for molecules and ions containing nutrients and regulatory substances that circulate among cells, through cell walls, and within cells. Furthermore, water participates in most of the biochemical reactions occurring in organisms. This participation is possible because water can ionize substances, and the resulting ions are required by cells for their energy-producing processes. The chemistry of living systems is largely developed around water's solvent properties. To understand why water has so many unique features which make it so fit to support life, we have to examine its bounding. The water molecule has two hydrogen atoms, each bound to an oxygen atom. The essence of these hydrogen-oxygen bonds is the sharing of a pair of electrons between each hydrogen atom and the oxygen atom. The electron distribution is represented symbolically here by the black dots. The more electronegative oxygen atom exerts a stronger pull on these bonding electrons, and they tend to be drawn more towards it. The increased electron density around oxygen gives oxygen a slight negative charge, and the decreased electron density around the hydrogen atoms makes them slightly positive. The resulting polarity of the molecule allows a hydrogen atom of one water molecule to be slightly attracted to an oxygen atom of another water molecule. This attraction is called hydrogen bonding and is directly responsible for all of water's unusual life-supporting properties. Water has a high heat capacity because the hydrogen bonds absorb added energy by vibrating, rather than having that energy increase the speed of water molecules, which would increase the water's temperature. Water has a high heat of vaporization because hydrogen bonds must be broken before water molecules can make the jump from the liquid to the vapor state. Ice floats because the water molecules pack themselves in an open hexagonal crystal structure held together by hydrogen bonding. As ice melts, the amount of more tightly packed non-hydrogen bonded liquid water increases. The liquid is therefore more dense than the solid. Hydrogen bonding is also directly responsible for water's high surface tension and its remarkable solvent properties. The polar water molecule is able to surround negative and positively charged particles called ions. These ions, insoluble salts, are then able to break away from the crystal surface as the compound dissolves. The ions are said to be solvated by the water molecules. And so we can see that water is a very special molecule, unusually fit to support the process of living. And nature continually recirculates and purifies water in the hydrologic cycle. The next few slides tell a picture story of this hydrologic cycle. We begin in Yosemite with the spring thaw.